Hello, my name is Philip Archuleta, and I am the CAM2 Fair Vision team leader. This video will briefly summarize my personal contributions to the team throughout the semester. First, let me explain some general information about the team. Within the CAM2 Fair Vision team, there exists two distinct subteams: the Generative Adversarial Network subteam, otherwise known as the GAN subteam, and the Fairness and AI subteam, otherwise known as the FAI subteam. Each of these teams is working on a separate project and therefore have separate problem statements. For the GAN subteam, the problem statement is as follows. Researchers claim synthetic images can mitigate unfairness in computer vision, but we don't know the performance on that. For the FAI subteam, the problem is computer vision is biased towards human, action, and environment when applied to factory safety due to biased training data. And, as a quick definition of bias, bias is the overrepresented features in an image dataset, in the case of faces, age, race, and gender, used to train an image classification algorithm. So, why are solving these problems important? Well, better image identification algorithm training data leads to more accurate image identification algorithms, which in turn leads to improved fairness in computer vision. The GAN team aims to train GAN models utilizing a real dataset such as Fairface. These GANs will input a feature matrix, which is a series of latent vectors corresponding to particular features such as race, age, and gender. The goal is to control the features of the output images of the GANs in a way that the dataset is balanced, defined as 50% male, 25% white, 25% black, 25% Asian, and so on. These theoretically fair and balanced output datasets will be inputted to DeepFace, a facial recognition algorithm. DeepFace will attempt to identify another set of real images, and the accuracy of this process will be compared against DeepFace trained with a real dataset. Given that I just discussed the GAN subteam's methodology, I would like to highlight an important related work, Too Biased or Not Too Biased by Robinson et al. The idea of a demographically balanced dataset being fair is derived from this publication, as their key finding was that if a facial recognition algorithm is trained with demographically balanced real face images, the result is a classification algorithm that is highly effective. This defines the evaluation of the GAN subteam's methodology, with our main contribution being generating an algorithm to modify latent vectors in such a way to control the demographics of the GAN outputs. The FAI subteam plans to first acquire unbiased training data in the form of real videos of persons operating factory equipment in a safe manner. Employing this unbiased training data, a neural network model will be constructed to actively detect in real time if a worker utilizing a machine is not following the most safe practices. This model will be deployed in real factory settings and its effectiveness will be analyzed. Now, for a brief summary of my personal technical contribution to the team. I ran Lime, an explainable AI program, numerous times with different configurations, each corresponding to different image classifier. The data output for these Lime runs were confusion matrices, as shown on the screen, with the cell scores being the probability of a certain image classifier detecting an image as that image and not another. These matrices were utilized to determine which image classifier was the most effective, with effective being defined as a high diagonal score and a low outside diagonal score. With confusion matrices corresponding to each image classifier in Lime, I was able to work with Austin and Esteban to analyze each matrix to determine the image classifier's effectiveness compared to other classifiers. With this, I was able to narrow the 7 potential classifiers of use to 2. The goal was to find the best classifier, and this was accomplished later by Austin. This work was discarded when the GAN team ultimately changed its focus to its current state of methodology. Utilizing Haobo's GTX 1060 on my local machine, I was able to run and train DC-GAN with the following outputs. Visually, the produced images appear disfigured. However, this is not a quantitative form of evaluation, and we'll get to that in a couple of slides. Tina and I both ran DC-GAN with the same configuration settings, although on separate machines. My outputs are shown on the left, while hers is shown on the right. The products are identical when quantitatively evaluated with a metric known as Frechet Intercept Distance, or FID, shown on the next slide. FID is a quantitative metric that calculates the distortion of a given image compared to a desired image, in this case real faces. FID was not my personal contribution, rather it was Anid's, so I will not go into too much detail about it here. The yielded FID score for these DC GAN outputs was 39.05, but what does this mean? As seen by the paper, How Good Is My GAN, by Smekalov et al., 39.05 is a reasonable FID score to expect given that they yielded a score of 41.8 in their paper. Lower is better here, and this paper concluded that 41.8 was still too high to define the output of DC GAN as quality, although they indicated that 20.6 WGAN GP score was low enough to consider it usable. They do not provide a stated FID score threshold in this paper, but we can assume that 39.05 from our DC GAN output is too high to consider the quality good. Looking to improve the results of DC-GAN, we hypothesized that trading it with more epochs on a faster machine like Argon could do the trick. My task was configuring and using the Argon subsystem, but first I had to determine how. I learned that there is a free layer of process to accessing the machine, first SSHing in from a terminal, and then requesting a job node from a login node, as depicted in this figure. A main question of mine was how to set up an environment on the job nodes, given that the syntax was one I had never experienced before. Eventually, I was able to set up Anaconda on the system and began testing DCGAN. Results showed that, with two NVIDIA Tesla K80 GPUs per node, running on the job node yielded a 97.67 day runtime. This was incredibly surprising. Tina's EE220A known runtime of DCGAN was a mere 2.79 days, so how could local be approximately 35 times faster than a supercomputer? The determined answer is that, while local is faster, acceleration of DCGAN as it runs could reduce the expected 97.67 day runtime significantly. Still, how is the EE220A machine faster? Well, DCGAN is optimized to run on one GPU, and the Titan X, with a faster clock speed and more transistors than a Tesla K80 as shown in the figure, simply does a better job. With this information, we eliminated DCGAN from use in the project. With Argon work on DCGAN completed, I transitioned to ATTGAN. I performed a full timing analysis, tweaking both the amount of GPUs used, represented as nodes, and the processes per GPU, represented as processes per node. The result here showed that, no matter the GPU count or processes per GPU, ATTGAN averaged 1 iteration per second in epoch training on Argon. Haobo's local machine with a Titan X had a runtime per epoch of approximately 3 iterations per second, which, like DCGAN, shows that local is faster than Argon. This clearly demonstrates that the strength of Argon lies in multi-GPU tasks, which it is clear that ATTGAN is not optimized for. ATTGAN was running on a singular Tesla K80, which, as previously explained per the figure on the slide, it is not as powerful as a Titan X. ATTGAN is incredibly promising in controlling demographic features, however, so next semester's work will likely focus on optimizing ATTGAN to run with multiple GPUs, such that Argon can be used with it. Now, for a brief summary of my administrative personal contributions to the team. Every week, I formulate the itinerary and lead our weekly Tuesday meeting, paying special attention to ensure that it is not rushed and that all team members have a speaking contribution. In addition, I work with Xiao and Moya to determine the weekly tasks for every team member. I coordinated with Xiao and Moya to revisit our project focus, eventually reaching what I presented in the first couple slides. We spent time determining 1, if the project focus of the prior crowdsourcing team was innovative enough to meet the CVPR publication that we were aiming for in November, and 2, if not, did we have enough time to make modifications? After discussion with the entirety of the team, I ultimately pulled the trigger on retooling our project focus to the one stated in the methodology of the GAN team. I worked with Xiao and Moya to create a draft for Amazon's AWS funding proposal, and I contributed mainly by reducing Xiao's Sony funding proposal from 13 pages to 5, only considering acquiring unbiased training data in the form of videos of machine use in workplaces, rather than the full workflow detailed in the Sony proposal. Additionally, I edited sections as needed, and subsections were moved around in compliance with Amazon's template. I worked with George to draft a section in his Argon Access extension request about what we plan on using the machine for. This request was ultimately approved at the beginning of November. Everything I have done has been documented on the team's Google Drive, and the work contributed this semester will be invaluable in accomplishing the team's goal of a publication. I believe I deserve an A, based on the fact that this semester's work will lead to a publication, both through my individual accomplishments and my leadership. Once again, I do really appreciate the opportunity I have been given by Gore, Kai, and Dr. Liu in being able to lead this team. It's probably the thing I am most proud of since I've been at Purdue, and I think about every day how I can push my team to new heights. Once again, thank you for the opportunity.